Okay. So we're in, where are we? We're chapter 2.3 today, right?
Yeah.
What we will do is, when we take a quiz over 2.3 and 2.4, which is what I want to cover today, the quiz will also include 2.2. Okay? So we'll have something for 2.2. Like I said, we're short on time, and so please, try to be here on time so that we can jump right into our taking our quiz. And I'm probably just going to have to say, if you're not here on time, you're just going to have less time on your quiz, just because we're just so strapped for time. We don't have much time. All right, so let's see if I graph. Of course, losing the markers takes me so long. There we go. All right. So let's say if we graph this here. If I graph f of x equals 6x cubed minus 19x squared plus 16x minus 4. If I actually graph that in my graphing calculator, if you want, some of you guys can punch that in if you want to. Somebody want to do that? Do that for us, William, and tell us if there's any spot that it looks like there's clearly a zero. In other words, when I say where are the zeros of this function, what am I actually asking for? The what? The x-intercepts, right? The zeros are the same thing as the x-intercepts. So if you graph this on your graphing calculator, is there anything where it looks like it's the whole, like an integer, where it crosses the x-axis? Anybody get one? Or is your window too narrow? Do you see one? They show the graph in the book, and so it should look something like this. You should see something around here in this area of the window where it looks like the graph kind of comes up and does this number here, and then you should see another portion that comes up this way, and that should look like it's around x equals 2. You guys see that? Huh?
You have to make the windows small. We have all of this.
Yeah, you have to kind of make it smaller. But you see how it splits up there? It looks like it goes right through the x-axis at around 2.
Yeah.
Right? So sometimes it can be hard to tell exactly where it's crossing on a graphing calculator, right? But you can use the graphing calculator to sort of estimate. So if I look at this, it looks like x equals 2 is probably a 0, right? That means if I set this whole thing equal to 0 and factored it, one of my factors should be what? 2. But how would I write that with like the x term in there whenever I break it apart? X equals
x or x plus 2.
I mean x what? You said x plus 2? If it's x plus 2 and I set that equal to 0, what does x end up? Not equal to 0. I don't know why I did that.
You said like solving for it?
Would this be my factor if x equals 2?
No.
No, what would my factor be?
X minus 2.
X minus 2, right? So if x equals 2, if that's one of my x-intercepts, then that means that this has got to be one of my factors, right? Does everybody remember that? We talked about that last time, how those are all kind of the same thing. The zeros and the x-intercepts and this being a factor, those are all the same thing, right? They all mean the same thing. So if that's the case, what should happen is that I should be able to divide this guy, this function here, by x minus 2, and I should get a remainder of 0. Right? If you think about the way that multiplication and division works, if 2 is a term of 6, right, then I should be able to divide 6 by 2, and I get a remainder of 0. And sure enough, I do, right? So have you guys done long division with polynomials before? You've seen that, all right? So let's just do that. Let's check it out. What's that?
You're doing long division with unfinished equations now?
You've never done long division with polynomials?
No, I have. I hated it enough in 4th grade. Didn't come back and revisit it.
It's been a while. So this is why you learned it way back when, right? Because you were going to see it again today. They were trying to prepare you for today. So let's try it, all right? So x minus 2, we're going to divide that into 6x cubed, minus 19x squared plus 16x And if you haven't seen this in a while, you need to think about, how you do long division with just numbers without the variables in there. It basically works the same way. But we look first to see how many times will our x term go into 6x cubed, and so that's going to go into that 6x squared times. So we write that here over our x squared term here. So we just multiply through by everything. 6x squared plus times x is 6x cubed. 6x squared times negative 2 is negative 12x squared, right? And so then, just like we would do in long division with numbers, we subtract this term from the term above it, and so these cancel out, and so this gives us negative 19 minus a negative 12 is going to give us a negative 7x squared plus 16x. X will go into that, minus 7x times, that's negative 7x squared. Negative 7x minus times negative 2 is going to be positive 14x. And so again, we subtract, and we're left with 2x here, minus 4, and then that will go into, x will go into 2x, x will go into 2x 2 times x is 2x, 2 times negative 2 is negative 4, and we get 0, right? Yes?
How did you get 16x plus 14x equals 2x?
Because you subtract.
I subtract, right? So whenever you do long division, if you have like a number, if you're dividing 946, divided by 3, then what you're doing is you're taking the 3 will go into 9 3 times, and 3 times 3 is 9, and so you subtract out the 9, and you get 0 right there, and you bring this down and get 46, right? Whenever you do long division. And so we're doing exactly the same thing here. We're trying to multiply this times a term that's going to give me the same number here, right? And give me the same number here, so that whenever I subtract those, so all of this, when we come down here to this step, we basically put a negative in front of all of that, right? Subtract all that out.
Oh, yeah.
Right? Alright. So we got 0, and that's what we should get if indeed x equals 2 is a 0 for this function. When we divide x minus 2 into it, we should get a remainder of 0. Alright? So that's another way, that long division is another way that we can determine the zeros for a function. Alright? If we have a non-zero remainder, then it means that it is a factor. If we don't have a 0, like let's just say we did all of that and this turns out to be, we get the number 2 at the end. We would do the exact same thing that we do when we have a, let's see, I'll use an actual example, because I've written that down in my notes and it'll keep me from making a mistake. If I divide, for example, x squared plus 3x plus 5, if I divide that by x plus 1, I get x plus 2, but then I get a remainder of 3. And so what we do with the remainder is we say plus 3 over whatever our divisor was. So that's how we would incorporate the remainder into our answer if we actually had a remainder in the problem. And that would mean that you could say that x squared plus 3x plus 5, if we wrote it out with all the factors, x plus 1 times x plus 2, which is this factor here, with a remainder of 3. We could write it like that. So that's two ways we could sort of incorporate the remainder into our answer. But let's do an example. Page 113. Well, we actually, never mind, we just did that. So we just proved that was a 0, so we don't need to do that one. So let me write out the division algorithm. Any questions about how we did the long division? Is there any step that you want me to review? Make sense to everybody? Remember, with the whole remainder thing, this is saying the same thing if you have numbers, and if you have 2 into 15, right? That's 7, which is 14 with a remainder of 1. So we would say, well, that means that my answer is 7.5, which is 7 plus 1, which is my remainder, over my divisor, which is 2. That's all that we did right here in this example. It's the same exact process. So the division algorithm, write that down. And it says, if f of x and d of x are polynomials, you know, again, if I'm writing any of these terms down and you're like, what's a polynomial again? Then don't just like ask that question and then let it disappear, right? Either ask it out loud so I can answer the question, or go back and look it up in the book and remind yourself what the definition is of a polynomial. So if f of x and d of x are polynomials and d of x does not equal 0, and the degree of d of x is less than or equal to the degree of f of x. What does degree have to do with?
The highest power.
The highest power of the x term, right? Of the x terms in the function. All right, so if all that's true, then we can say f of x equals d of x times q of x plus r of x. And so for this problem here, this is for the division, this is our dividend, which is the number on top, if we write it in fractional form, right? This is our divisor. So this is the number on the bottom. Q of x is our quotient. That's this number here, right? That's the number that we got on when we did 3 into 7, and we say this is 2, and this is our quotient, right? And then 6, we get a remainder of 1, so that's our remainder. We would say that's the same as 2 plus 1/3. This is the remainder out here. All right, so when we're working in polynomials, you could write it in this form.
What is the dividend? Like,
The dividend is this number.
number?
It's this number here.
Oh, it's the one that's under the
one that you're dividing into.
Okay, and then the divisor is the one on the outside.
That's this one here, yeah.
Okay, got it.
The one you're dividing by. And so for this, we could say that where r of x equals 0. Someone have a question? No? Where r of x equals 0, or the degree of r of x, that's the remainder, is less than the degree of d of x, which was our divisor, this number right here. So that's one way you can write the division algorithm. There's another way. Just an alternate way can also, and I'm just spelling all this out because you've got at least one homework problem where it asks you this. Can also write as f of x over d of x equals q of x plus r of x over d of x. So this may sort of make more sense to us with what we just did. So f of x is the function that we're dividing into, right? D of x is the function that we're dividing the top function by, right? Q of x is what we get on top of our long division, right? So this is the result, basically, that we get. And then our remainder is the remainder over our divisor, this down here. But if you notice, when you look at it in this form, if I multiplied every term in this equation, if I multiplied both sides of this equation by d of x, I get this. You guys see that? It's the same thing. So I can easily get one from the other. I could either divide everything by d of x to get it in this form, or I could multiply everything in this form by d of x to get this form. All right? So just a recommendation, you need to do this or you're going to have trouble with long division. Whenever you've got a long division problem, make sure that you reorder. If your terms aren't ordered from highest power to lowest power, make sure you rearrange your polynomial so that it's set up like that. All right? Descending powers of the variable. And if you're missing, so before, I guess let me just write this down. We're doing long division. Two things. Write variables in order of descending power and put a zero coefficient for any missing variable terms. What do I mean by that? I mean if one of my polynomials are this, like if I'm dividing into this, then change that to x squared plus 0x plus 4. Right? Before you do the long division. All right, let's do another example, page 115, and let's see what that says. Um, 8x cubed minus 1 divided by 2x minus 1. So 8x cubed minus 1 divided by 2x minus 1. Right? So the first thing we want to do is when we're writing our dividend here, we're going to put 0 coefficients in front of all the missing x terms. So we're going to write it like this. And then we'll put our divisor out here. Very good with that? So again, we're really, for this one, we just focus on the first term. How many times will 2x go into 8x cubed? It will go into that 4x squared times. So if we did that correctly, when I multiply this times this, I should get the same thing that I have right here. So this is 8x cubed. 4x squared times negative 1 is negative 4x squared.
What did you multiply? What things did you multiply to get the 4x squared?
Right here, 4x squared times 2x has to equal 8x cubed, if I did it correctly.
And then how did you get 4x squared in the first place?
But I looked at that, I said how many times will 2x go into 8x cubed?
Okay.
Right?
Yes.
So I don't really even pay attention to the second term here. I'm only looking at the first one when I'm trying to figure out what to put up top, right? What to put as my divisor. All right, so again, remember, this whole thing is subtracted from whatever the top number is, right? So 0 minus a negative 4 is going to give me a positive 4x squared plus 0x minus 1. 2x will go into 4x squared 2x times, so plus 2x. This is 4x squared. 2x times negative 1 is negative 2x. 0 minus a negative 2 is going to be plus 2, so we've got 2x minus 1 here, and 2x minus 2x minus 1, this whole thing is just going to be, we can see that these are the same, so we can just skip right to this point. That's going to be a plus 1 there because 1 times this will give us 2x minus 1 and give us a remainder of 0. So our final answer is 4x squared plus 2x plus 1. Does that make sense to everybody? I don't know why I put the 1 over here. Sorry, I should have put the 1 right here. Should I? Why does that look weird? Oh, I'm looking at the wrong thing. I was looking at my 0 up top. I need to be looking at this. Sorry. It's easy to get confused. There's a lot going on, right? Everybody see how I got 0? All right, so then what does that mean is actually a 0 of our function. For the function 8x cubed plus 8x cubed minus 1, because we did the long division here and we got a 0 remainder, then what is actually a 0 of this function?
2x minus 1.
2x minus 1 is a factor.
1.
And so the 0, if I set this equal to 0,
1/2.
it would be 1/2, right? I would rearrange that and I would get x equals 1/2. So 1/2 is my 0. Make sense? Yep. All right. Cool. How are we doing on time? We get out at 12, right? No. I think we've got time. Maybe not. The next one does the same thing, but we come up with a remainder, right? And so I'm just going to write down. I'm not going to go through all the steps, but I just want you guys to understand that the next one does x. Let's see. X squared. You can do a longer polynomial. X squared plus 2x minus 3. We have this divided into 2x to the 4th plus 4x cubed minus 5x squared plus 3x minus 2. And so when you do the whole thing, you come up with an answer of 2x squared plus 1. And you end up getting a remainder down here at the bottom. When you subtract everything out, you get a remainder of x plus 1. All right, so the way that we would write that answer would be 2x squared plus 1 plus x plus 1 over x squared plus 2x minus 3. So this was the number we got on top, right? This was our remainder, and it's divided by the number that we were dividing the original polynomial by. Or it's over the number we were dividing the original polynomial by. All right, so we need to talk about synthetic division. Any questions about this? Does that make sense? Adam, you shouldn't sit at the front because you always go, yeah, that makes sense. And so I'm like, what about anybody else? You're like, right, you're the first one I see. All right, synthetic division. Not Dixie-ision. Synthetic. It's living in the South, living in Dixie. All right, so if we have a polynomial, for example, 8x cubed plus bx squared plus cx plus d. So that's a trinomial because the highest power is 3. And we divide by x minus k. You can use something called long division, which is kind of a shorthand way to do what we're doing over here. All right? And so the way that you do this is you take all of your coefficients from the original polynomial, and you take, this only works whenever this term here is in the form of x minus k. What does that look like?
X minus 2 or x.
Yeah, it looks like when we would factor a quadratic or something, it looks like the factored terms, right? It looks like when we talk about we have a 0, if 2 is a 0, then we can say that x minus 2 is a factor, right? So it looks like one of those terms. So if we're dividing, we're basically figuring out, is this number a factor of this bigger polynomial, okay? And so the shorthand way to do this is we say, you take your a here and you just bring it down here, and then you do k times a. So that's what you put right here, ka. And then down here, you subtract the ka from the b. So this term here is like b minus ka. And then you just keep doing that. I'm going to draw an arrow there like that. You keep doing that where you take the term here, and you subtract whatever term is here, and you bring that answer down. And then you take this, and you multiply it by this, and you put that back up here. So you just kind of keep doing that all the way across. And this is going to be a lot easier to follow when we do an example. But what happens when you do that is that this that you get in the very last section, as your very last answer, this is going to be your remainder right here. And these, whatever these, this is not a 0, by the way. Remember, if I don't put a line through it, it's probably not a 0. Sometimes I forget. This is just saying whatever that term is there. These values here end up being our coefficients of our quotient. So the polynomial we get after the division is complete, and then this will be the remainder. All right, so let's see an example of that, because it's much easier to follow if we have some actual numbers to work with. So page 116, we're going to use synthetic division to do x to the 4th minus 10x squared minus 2x plus 4. And we're going to divide this divided by x plus 3. Alright? So we're going to write it just like we wrote it over here. Our k term is what?
-3.
-3, right? Because we're dividing by x minus k, so since we're dividing here by x plus 3, then this term is -3. And then we take all of the coefficients from our polynomial up top here. So we've got a 1 coefficient on the x4, a negative, we need to put a 0 in there, right? Yes. We're missing the x cubed. So there's an x cubed in here, right? Plus 0, x cubed. So we put a 0 here. -10, -2, +4. Now, does everybody know where I got those numbers? Or were you just like, that's magic? There's no magic in here, right? There's an explanation for it. So if you look at it and go, what's that magic? All right, there's the asking me so I can explain the magic. I'm not a magician that hides my secrets. Okay. You guys follow me? We good? All right. Diego, are you still awake?
Yes.
Okay, I couldn't tell if you were looking at the book or if you took a brief nap. All right. All right. So now what are we doing? We're just going to bring this term down. Right. We're basically taking whatever's on this row. We're going to subtract it from the row above. So kind of think of it being an understood 0 here. Right. 1 minus 0 is going to give us 1. Then we take the -3 times the 1 here, and we write that here. -3 times 1 is -3. All right. 0 minus -3 is
-3.
minus -3. Are we subtracting or are we adding? Did I tell you wrong? I did. Thank you.
Right, added.
Yeah, I'm adding. My bad. So you're right. I told you this was confusing. So we're adding here. Think of this as plus. -3 times -3 is 9. -10 plus 9.
-1.
-1. -3 times -1 is 3. Combine these together, you get a +1. -3 times +1 is -3. Here you get a +1. All right? So this is our new polynomial, right? Coefficients of polynomial. This is my remainder. Right? So I would write the answer as x. We've got three terms here, so x cubed minus 3x minus x, minus 3x squared minus x plus 1 with a remainder of 1 over x plus 3, because that's what we divided the whole thing by. Did I get that right, Emma? Okay, all right. You did correct me on that, so we need to get you on the board here. All right. Does that make sense to everybody? Again, we can only do this if we're simply dividing by x plus or minus some term, right? But that's what we are dividing by when we're trying to figure out if it's a zero, right? So there'll be a lot of cases where we can just use this synthetic division to find out very quickly if we had a zero. Is x plus 3 a zero of this equation? Of this polynomial? Is negative 3 a zero of this polynomial? It's not. Why not?
Because there's a remainder.
Because we have a remainder, right? This has to be 0 if it is in fact a 0. All right?
So if you did that with the factor, you would just, it would be the exact same thing, but you wouldn't have the remainder.
That's right. You would get a 0.
So it works for factors too, not just non-factors.
Yes, that's right. Anything, right? It's a way that you can check to see if it is a factor. And so that's actually what our next theorem says here. Basically applies what we just said. The remainder theorem says that if f of x is divided by x minus k, the remainder is r equals f of k. In other words, what is k in this equation? When we're doing that problem? Negative 3, right? This is our k here. So what the remainder tells us is that if I take this negative 3 and I plug it in my original polynomial, my value, the value that I'll get is this remainder value. So negative 3 plugged in here should result in a 1. All right? Now, if I'm thinking about the graph of the function, what does that mean as far as the graph of the function goes? It's not a factor. We haven't found a 0, but we did find something that's useful for this function as far as the graph of it goes. We've just discovered that there is a point on my function at negative 3, 1. Right? Because I could write this as y equals this. So if I plug in negative 3 as my x value, my y value is 1. Does that make sense to everybody? So these are all like kind of pieces that they should be as becoming assembled in your head, right? And it's starting to kind of those things are clicking. All right, so in addition to the remainder theorem, there's also the factor theorem, which is what we were talking about a minute ago. And the factor theorem says this. Polynomial f of x has a factor of x minus k if and only if f of k equals what?
0.
0, right? If I can substitute in the k and I get 0, in other words, I get a remainder of 0, then I know this is a factor. I just realized I wrote something down wrong in the notes, so let me correct that real quick. Okay. So if your remainder is 0, you know that you found a factor, or a 0, or an x-intercept, right, of this particular polynomial function. We're running out of time, so I'm just going to say that statement and hope it sinks in and makes sense, right? If you get 0 for your remainder when you do synthetic division, then you just found a factor for your polynomial, you just found a 0 for your polynomial, and you just found an x-intercept for your polynomial, right? What is my x-intercept? If this was 0, what is my x-intercept?
The K, whatever K is.
Whatever k is. In this one here, it would be -3, right? All right? And it would mean that x plus 3 is a factor. And it would mean that -3 is a 0, right? All of those things are true, all right? Like I said, like we also said with this one here, if we don't get 0, we have found what the y value is for this function at this x value, okay? All right, and that's on 118. Like I said, for time's sake, we just need to keep chugging along, but at the bottom of 118, there's using the remainder in synthetic division. That's kind of a restating of the things that I just told you. All right, the rational 0 test, let's talk about that. The rational 0 test, so we have a polynomial. If we have f of x equals a to the n, we're going to write it like this. We've done this before. A1 to the x plus a to 0, right? So this is kind of like a way we could write out a polynomial with just variables. So if you have this, I'm sorry, no have. If this function has integer coefficients, what do I mean by that?
Real number coefficients.
Not just real, not
So like negatives, positives, zeros. I just think it means no fractions.
no fractions. That's the key, right? If it's an integer, there are no fractions. They're all like 1, -1, 2, -2, 3. There's numbers like that, right? Integers are just
It means no decimals either, right?
no decimal, no fractions, right? Then every rational 0 of f is of the form rational 0 equals p over q, where p and q have no common factors other than 1, p is a factor of a subscript 0, and q is a factor of a subscript n. Yes.
It says P is a factor of what?
P is a factor of a sub 0, so this term right here. Okay? I know I usually write my zeros with a slash, but it was already kind of tiny. So to restate this, I wrote this, because this is basically what all of this is saying. That if I have a polynomial function with only integer coefficients, then I can say the possible rational zeros, and if we make it to the next section, which we have to, then we'll say what we mean, the difference between rational and irrational. It will be the factors of the constant term, which are this, is that term, over the factors of the leading coefficient, which is this term. Okay? And so what it means, these are just possible zeros, right? We have to test and see if these are in fact zeros. But what it means is if I give you a function like this, then the possible zeros are all of the factors of the constant term. So the factors of 3 are what?
1 and 3.
1 and 3, right? They can be plus or minus. So we say plus or minus 3, comma, plus or minus 1. All right? Divided by the factors of our leading coefficient, which is 2, which is either plus or minus 2 or plus or minus 1, right? So for this one here, the possible zeros for this function would be, I'll write them out in the order they did it in the book. We're just looking at all the possibilities here. Plus or minus 1, right? That would be the 1 over the 1. Plus or minus 3, that would be the 3 over the 1 down here. Plus or minus 1/2, that would be the 1 over the 2 here. And then the other one would be the, which one are we missing? The 3 over the 2, plus or minus 3/2, right? And so those are all of our possible zeros for this function. That's the rational zero test. It just gives us a starting point, right? It's not saying all of these are zeros, it's saying here's some things you can try because some of these are going to be zeros. All right, these are the possible rational zeros. So if I know these are the possibilities, how would I actually test to see if it is a zero? What have we learned today to be able to do that?
Put it in as x minus 3 or x plus 3.
So if we plug it in,
X equal to, then put it equal to 0.
so if we plug it in, it will be equal to 0, right? So we could do that. We could plug it in, see if it's equal to 0, or we could do synthetic division and see if we get a remainder of 0, right? Both of those will give us 0 if we plug that number in. So in the book, they did synthetic division. They started with the number 1, right? And sure enough, if you do, we'll just do that just to practice our synthetic division, right? We take all of these values, 2, 3, -8, 3, bring our 2 down. 1 times 2 is 2, 3 plus 2 is 5, 1 times 5 is 5, -8 plus 5 is -3, 1 times -3 is -3. We get a remainder of 0, right? Or, like Adeline said, we just plug in, we say, what is f of 1? Into our function, and if we plug in 1 for each of our x terms, we get 2 plus 3 minus 8 plus 3, and that's 5 minus 8 is -3 plus 3 equals 0, right? So either of those methods would work, and that tells us that 1 is a 0 of this function, right? Now, where long division helped us here is now we can easily find the other zeros without having to guess. How would we do that? Anybody know? is because what long division just told us was that this function, if I set this function equal to 0, if I said 2x cubed plus 3x squared minus 8x plus 3 equals 0, and I did long division and got 0, and when I used a factor, when I used a 0 of 1, then that means that x minus 1, right? That would be my factor term when my 0 is 1. X minus 1 times what we got here with long division, 2x squared plus 5x minus 3 equals 0. Okay? And now I've got a quadratic that's a pretty simple quadratic that I could factor, right? And figure out what my other zeros are, if I can talk. And so that is, we've got a 2x term, and we've got an x term here, right? And the possible factors of 3 are 3 and 1. One's negative, one's positive. We need to end up with a positive 5 here, so we want to have a positive 3 times my 2, so we'll put a positive 3 here, and we'll have a negative 1 here. And I can double check that, use the FOIL method just to make sure I get that, right? But now I know what all my zeros are. My zeros are x equals 1, this one would be x equals 1/2, and this one would be x equals negative 3. Right? Did I lose anybody in doing that? I know we're going a little fast, but we're just, I've got to get to imaginary numbers. Hopefully you guys have seen that before, so it'll be pretty quick. Left a bad taste in your mouth? All right. So I think Descartes' rule of signs, you can look at that in the book if you want to. That's on page 121. And it just has to do with the fact that if you've got your polynomial set up like this, based on the number of times that the sign flips from positive to negative or negative to positive, that'll help you guess how many real zeros there are. We're just out of time, and that's not really. I don't even know if you do any homework problems that specifically use Descartes' rule of signs. So I'm not going to go over that. Let's go on to section 2.4. So some quadratics have no real solution. And meaning they only have imaginary solutions, right? So for example, x squared plus 1 equals 0. Can we find a real 0 for that function? No, if we try to solve for it, we get x squared equals minus 1. Then we take the square root of both sides, right? So we get x equals plus or minus. We got a negative number underneath the radical, right? And it's an even radical, it's a square root. So the way that we represent this is we use the imaginary unit I, right? Where I equals the square root of negative 1. And so anytime I square I, what am I going to get? If I do I squared, what does that equal? If I equals square root of negative 1,
Negative 1.
I squared equals negative 1. If I square both sides in this equation here, I get negative 1, right? So that's going to come into play as we start doing some multiplication with this I term. All right, so you guys said you have seen this before, right? This isn't the first time. So we call these, when you've got this I term in there, we call these complex numbers. Numbers with I are complex numbers. So if you see that term, that's what we're talking about. Numbers with an imaginary term in it. And can be written as standard form. This is the standard form for a complex number as a plus bi. So if I have a number like this, and I say I want you to write that in standard form, right? That complex number in standard form, then you would say, you would bring the 9 out, and the square root of 9 is 3. So you could think of this, first term here as the square root of 9 times the square root of negative 1, right? Could we rewrite that like that? Minus 5. And we know the square root of 9 is 3. And we know that the square root of negative 1 is equal to I. Right? Minus 5. And then to write it in standard form, we would just reverse that, because the a term comes first, the non-imaginary, the real term comes first, so we would say negative 5 plus 3i. That would be that imaginary number in standard form. Now, when we've got two complex numbers, we can say that those two complex numbers, a plus bi and c plus di, are equal. I just don't know what my brain thinks sometimes. Equal. You guys don't even enjoy those jokes because you're not even where I am writing it down, but I get concerned about myself. One day I'm just going to fall down on the floor, guys. Call 911 if that happens, okay? And E equals C, and B equals D. So if we're proving that two complex numbers are in fact equal, then we have to prove that the real terms are equal and that the imaginary terms are equal, right? Or the coefficient of the imaginary terms are equal. Any questions as you digest all of that information? All right, so let's talk about adding and subtracting complex numbers, which you've probably seen before. Pretty straightforward, right? When you add a plus bi plus c plus di, we just add the real terms, a plus c, and we add the coefficients of the imaginary terms, right? You can kind of think of I as a variable. Right, just like 2x plus 3x is 5x, 2i plus 3i would be 5i, right? So that would be adding. Of course, subtracting is the same thing, but with, you're taking a difference. So a plus bi minus c plus di equals a minus c plus b minus d. Like I said, it would be exactly the same thing if we had like 3 plus 2x minus 4 plus 4x, right? We would take the difference of the numbers that did not have an x, that had no variable. We would say that would be -1 minus 2x. That would be exactly the same if we replace those x's with i's, right? So nothing really crazy if you just kind of think of the I as being a variable. So let's see, there's some examples. Like I said, we could do B and C just to make sure you understood. Yeah. So if we do 1 plus 2i minus 4 plus 2i. Stop a minute. Catch your breath. Very good. You guys surviving? Wait to make sure everybody's with me. All right, so we're just going to do 1 plus 2i minus 4 plus 2i. And so how would we do that? We would do 1 minus 4. Those are our real numbers. 1 minus 4 plus 2i minus 2i.
Or 2 minus 2, and then I on the outside works, right? Because that's what is in the formula.
Yeah, you can do that. You can think of it that way. Absolutely. So this is -3 plus 0. So our final answer would be -3. So just to show you that when you combine these imaginary numbers together, you may get a real number, right? The imaginary portion may go away. So that's a possibility. That's not out of the ordinary. And you can have the opposite, right? You can have all of the real numbers go away, and you're left only with the imaginary portion. So let's see one of those. 3 minus -2 plus 3i plus -5 plus I, right? So again, I think the simplest thing to do is just kind of think about this like any other variable term, right? So you've got 3, we could rewrite this as 3 plus 2 minus 3i minus 5 plus I. We could rewrite it like that. Combine like terms, 3 plus 2 is 5, 5 minus 5 is 0. So real numbers go away, and -3i plus I is -2i, so our final answer is -2i. So everybody gets what I'm saying when I say just think about the I as a variable, right? If you do that, you won't get mixed up. The only kind of catch with the thing that you have to remember that's unique about the I is that if I get I squared, what is that equal to?
-1.
-1, right? So if we happen to do a multiplication or a division problem and we come up with an I squared term, then make sure you change all of those I squared terms into -1s, right? So let's do some of those. When you multiply, let's see, you just use the FOIL method like we've used when we're dealing with variables. So example 2, let's see, where's that? Here we go. Example 2, I want to do A. So 5 minus 2 plus 3i. 5 minus 2 times minus 2 plus 3i. Again, just think of the I as an x term. So you just use the distributive property like you would if those were variables. So 5 times -2 is -10 plus 15i. Right? Straightforward enough. Nothing complicated about that. If we have 2 minus I times 4 plus 3i when we think about those i's as being variables, we would use the FOIL method to solve this. So first terms, 2 times 4 is 8. The outer terms, we have a positive 6i. The inner terms, we have a negative 4i. And then the last terms, we have a negative 3i squared. And so that's where this is important, right? Because we're not done until we take our I squared term and turn it into negative 1. So that's 8. We combine these like terms here to get plus 2i minus 3 times negative 1. So that's going to give a positive 3 on the end there. We combine that with the 8 to get 11 plus 2i. Any questions about that? Now, when you do this one, this is another multiplication problem. But notice with this problem here, these are almost the same term except for what? The same terms except for what? The negative in the middle, right? One's got a positive and one's got a negative in the middle, all right? Well, think about when we had something like this, 2 minus x, 2 plus x. More commonly, we recognize it like this, right? What does that always end up being? You guys remember? No? It'll be the difference of 2 squares. Do you guys remember that? So like when you multiply these together, you get x squared minus 4. So you can always factor the difference of 2 squares as this, right? So that's what we expect to happen here too, right? Do you see that? And so sure enough, if you did it the long way, if we did the FOIL method, we got 9 plus 6i in the middle, minus 6i minus 4i squared. And so these terms go away, and our I squared turns into negative 1. Whoops. All right, so we get 9 minus 4. The difference of 2 squares, but in this case, because they're both real numbers, we can combine those together and get 5. So the difference of 2 squares works a little differently because the I term goes away, and so you're able to combine all of your real numbers. And so this is a special, these two numbers together are kind of a special combination. They're called complex conjugates. And so complex conjugates are, it would be 2 imaginary numbers multiplied times one another in this form. And the reason this is important is because it gives us a way to get rid of that I term, right? To get rid of the imaginary number. And so we're going to do an example real quick that shows you. This will be, I guess this probably will be out of time. It's what we use whenever we're doing division problems. So I'm just going to show you an example real quick. So if we have a plus bi over c plus di, and I want to write this in standard form, which means I don't want a divisor, right? I want to get rid of this c plus di and put all terms on top and combine my like terms. Then what I would do is I would multiply top and bottom times the complex conjugate of the denominator. So I'd multiply top and bottom times c minus di. So that will allow me to get rid of that imaginary term on the bottom. All right, so that's kind of the trick for doing division. And there's an example of that at the bottom of page 131, and since we're just about out of time, I just don't have time to go over that. But you guys can look at that yourself. It's pretty straightforward. And that's how you'll get rid of the I term on the bottom. All right? One final thing, and then you should have all the information you need to do your homework. It's the principal square root of a negative number if A is positive, then the principal square root of negative A is square root of negative A equals square root of A I. Where I is outside of the square root. So I can have something like this, square root of negative 3 times the square root of negative 12. And that equals the square root of 3i times the square root of 12i, right? I could rewrite those like that. And so that equals the square root of 36 times I squared, which equals 6 times negative 1, which equals negative 6, right? So I can do problems like that. All right, so you'll have plenty of examples of that in your homework and have an opportunity to use this principal square root. Okay? All right, if you have any questions, like I said, I know it was rushed. Get used to this pace, because if we don't maintain this pace, we're not going to finish the material. So we kind of took chapter 1 sort of slow, and we're going to have to kind of, we've eased into pre-calc. We're going to have to take a little quicker from here. All right? You guys have a good day. Let me know if you have any questions. All right? I'm around during lunch.